This is the second video in a series of casing design overview. On the title page here, you can see my contact information. You also can see the link to the notes that I'm using to do this overview that are posted on Google Drive for your information. In this video session, I will be covering casing design equations, the criteria in which we do casing design. I will review the casing design factors or safety factors that we typically use. I will go over the general procedure for doing casing design work, and then I will end with the sequence or order that we probably should do our casing design activity in that will make it easy on us and not have to do our work twice. So in other words, you do the work in an order that makes more logical sense, and it makes it easier to get this work done. Okay, we're going to start with burst when we do casing design equations. The picture at the top represents, I call it half of a section, cross-section of casing with pressure on the inside and also a pressure on the outside. Now, burst is a load in which the pressure on the inside of the casing is greater than the pressure on the outside of the casing. Now, what this picture represents is that if we pressured up on a piece of pipe to the point that it tried to break the pipe apart in this manner, that would be, we would exceed the hoop stress that the rating of that pipe would break it apart in this manner. And that's what we're going to use to derive a pressure equation. So it has a pressure on the inside. It has a T, which is the wall thickness of the pipe. And it also is going to have a stress in this cross-sectional area, hoop stress in that cross-sectional area. So for thin-walled pipe, we can almost think is that the OD and the ID are very close to each other on something that is very, very thin-walled. So for something very thin-walled, if we take the pressure on the inside times the diameter of the inside minus the pressure on the outside times the diameter on the outside, that is going to equal 2 times the wall thickness times the stress. So that's just a force balance equation for hoop stress on this. And if we solve this for pressure, assuming that the pressure on the outside is 0, then we will get the pressure is equal to 2 times the yield strength times the wall thickness divided by the diameter, the outside diameter. And then if we assume a 0.875 manufacturing capability in controlling the wall thickness, which is what API standard is, we end up with the API burst equation by just putting 0.875 in front of this term. And so the pressure rating for burst API is 0.875, 2 times the yield strength times the wall thickness divided by the outside diameter. Now, this is a very, very conservative pressure equation. It utilizes, for us in the oil and gas industry, we use the minimum stress of the manufacturing range. I mentioned in the first video that the actual manufactured stress might be 15 to 20,000 over the minimum because they don't want to have any rejects. It's also based on the minimum wall thickness that passes API inspection, which is based on very old manufacturing capability. It only calculates the stress at the ID of the casing wall, which may be relatively thick for today's wells. So the pipe will actually only burst by getting the stress level required to fail the pipe to the OD of the pipe. Now here is I would say something that fits the condition of the API equation. Very, very thin walled member. This happens to be a soda can. And the wall thickness on this soda can is about 0.1 millimeter, or 4/1000ths of an inch thick aluminum. The aluminum yield strength is 40,000 psi approximately. It has a diameter of about 2 inches. And if we use the same formula, pressure is equal to 2 times the yield strength times the wall thickness divided by diameter. This soda can probably has a rating of in the order of about 160 psi. So if you can use this, and you probably didn't even know soda can was good for about 160 psi, but that's true. Makes you feel comfortable that it's not going to burst on us. And then we can take that relationship and expand on it if we would like to. We don't normally do this for all practical purposes in our world, but we can do this. And I'm not going to go through the mathematics of it, but the von Mises triaxial stress pressure equation is listed here for your information, and I'm not even going to attempt to derive it for you, but it takes 3 stresses involved. So it has not only the hoop stress, but it has so the hoop stress is trying to break it apart. That's in this direction. And then you would have the radial stress, which is in this direction, trying to, I call it rupture the pipe. And then you would have tensile stress, which is longitudinal along the axis of the pipe, which would be in this direction, would be the axial stress. So if you combined all 3 stresses, you get this equation. Now, all 3 stresses added together, you actually end up with a higher rating than using the API equation. So just to give you a little bit of a feel for this, the API equation is listed here, 0.875 times 2 times yield strength times the wall thickness divided by the diameter. That only gets you to the stress level at the very ID. So this very red is at the ID of the pipe, and the wall thickness of this pipe may be extremely thick. So it's not going to rupture the pipe because it's at the ID of the pipe, which is very thick, as the example I showed on the first video. Now, the von Mises equation takes into account hoop stress, radial stress, and axial stress, and it changes the direction. So the radial stress would be in the direction from the inside of the pipe towards the outside of the pipe. But if you put a little bit of a tension in the pipe, it changes this vector. So it rotates the direction of this vector from being completely horizontal to the wall to I call it an obtuse angle to it. And you can think of it this way, that the stress has to be greater than from the ID to the OD before this pipe is going to rupture. This distance from the ID to the OD, if there's no tension in the pipe, this is a shorter distance than the distance between here. If I've got some tension and you rotate this stress vector to an angle, it takes greater stress to get the stress to the outside of the pipe in order to rupture it. So that's kind of a visual way to think about that. A little bit of tensile stress actually increases the burst on the pipe, but we do not take that really into account. We can do a lot of sophisticated calculations with this it just gives us a better comfort factor, but we still do all of our design work based on a very conservative number, and that keeps us safe. It allows us to sleep at night. All right, now collapse is the fact that when the pressure on the outside of the casing is greater than the pressure on the inside of the casing. Now, collapse values utilized for casing design are empirical values. Now, when I say empirical values, means that you cannot always derive the number. So they're based on test data and not solely on mechanical equations. We can derive the two end-member equations for elastic collapse and for yield collapse, but the other two equations for transition collapse or plastic collapse, we cannot derive those. So the end result is casing is tested with I call it an API process for testing collapse, and you cannot have any failures. And so based on test data, we have equations that matches test data in which you will not have failures. So you don't have to really know a lot about this or try to derive it. All you have to do is be able to use it. So it boils down to you have diameter divided by wall thickness ratios. So you'll see that the elastic collapse equation is based on very large OD pipe, and it transitions from the very largest OD to smaller OD pipe, in which you'll end up with a smaller D over T ratio. So D over T ratio is decreasing as you go this direction. So elastic collapse equation would probably apply like for 20-inch casing. So it depends on the wall thickness, of course. And then transition and plastic would probably be applicable for like 13 3/8 and 9 5/8 casing. And then the yield collapse equation would probably be apply if you had something like some 5-inch thick-walled casing. That would probably be yield collapse equation would apply. You don't know necessarily which one of these equations applies. So what you can do if you wanted to would be to calculate all four values and see which one is the lowest value. Whichever one was the lowest value would be the controlling limiting collapse value for that casing. But you don't have to do that. You can just calculate a D over T ratio, diameter divided by the wall thickness ratio, and then you go into this table. So let's just say if you went into this table for P110 casing and you happen to have a D over T ratio that was, let's say, 17. If the D over T ratio was 17, that's between yield collapse and tensile collapse. So therefore you use the plastic collapse equation for calculating it. So you can calculate the D over T ratio, and that will tell you to go to the very formula at the beginning to use. Now you'll notice that in these transition and collapse, you have some, I call them some factors that make the equations work out, some F1 through F5, and you have to get these factors, empirical coefficients, from this table. So you'll get these coefficients from this table, and then you can calculate the collapse value based on the D over T ratio, the stress of the pipe, and the factors that the equation requires for you to calculate the value. So it's actually very straightforward. It's not very hard at all. Now, axial stress is actually just, we know that stress is force divided by area. And the stress can be based on either compression or tension load. So up at the top of a well, the structural pipe may have an extremely high compressive load because it's having to support all the weight of all the casing strings. But the majority of all of our tubulars, it's a tensile load. So tensile load is I call it the overriding axial load that we have to use in doing most of our design work. Now, I have created an application here that I'm going to ask you, if you want, would like to, would be to pause and then calculate this value. I say a string of 9 5/8 inch, 47 pound per foot, P110 casing was run and cemented at 10,000 feet. a 7-inch, 29-pound per foot P110 liner was run and cemented at 12,000 feet with an 8 1/4 OD by 7 1/4 inch ID tieback sleeve made from 110 yield material. And then this liner was tied back to the surface with the same 7-inch casing, requiring a 7 1/8 inch OD by a 6 1/8 inch ID tieback stem, also made from 110 yield strength material. Calculate the burst and collapse rating of both the tieback sleeve and the tieback stem using the API equations. So you can calculate that by calculating the D over T ratios, seeing which one applies for that size, and plugging the values into the equation and calculating the burst and the collapse values for these two sizes. So pause and do that exercise, help you make sure you understand these equations to apply them. All right. I have listed the specifications for 9 5/8 casing here. The 9 5/8 casing that I specified was 47-pound P110. It's listed here for your values, and I'm not going to read it to you. And then the 7-inch liner was 29-pound P110, and the values for that are listed here in this table. If we take a look at that exercise that I just made up, the OD of the tieback sleeve is 8 1/4, and the ID is 7 1/4. So it has a wall thickness of 1/2 inch. So the D over T ratio is 8 1/4 divided by 0.5, which is 16.5. If we look that up, we'll see which equation to use for collapse. But first we can calculate burst. The burst is 2 yield T over D. We're not going to downrate it for the 0.875 because it's a very pristine manufactured product that you can caliper and see that it's a 1/2 inch thick. It's made within 10,000ths of an inch. So we don't have to downrate it to 0.875. We can actually use the entire wall thickness. So it has using the API equation without the 0.875 in front of it, we get a value of 13,333 PSI, which is greater than the casing value rating for burst. The collapse value, since it has a D over T ratio of 16.5, which we calculated here, that means we need to use the plastic collapse equation applies. So if we plug in to the plastic yield equation, this is the equation that applies here for that, F1, F2, F3. We put those values in, and we get a value of 9,345 PSI as a collapse. Now you'll notice if you look at the table that this collapse value for the tieback sleeve is less than the casing. And I'll give a tidbit about that here in a minute. So I put a star on it because that value, collapse value, is less than the casing value. Now the tieback stem has an OD of 7 1/8 with an ID of 6 1/8. It also has a wall thickness of 0.5 inches, and its D over T ratio is 14.25. So the burst rating on that, if we plug the numbers into this equation and use the OD of 7 1/8, for the OD, we get a burst value of 15,400 pounds, which is greater than the casing value. So that's good. Now the collapse value for the stem, since D over T ratio is 14.5, the plastic collapse equation applies. Looking at our table up here, using this table, the plastic equation applies. We plug the values into the plastic equation, and we get a value of collapse for the tieback stem of 12,694 pounds, which is greater than the casing value. So the only one that was less than the casing value was the collapse of the tieback sleeve. And from a practical point, what you would have to manage during the execution of this is it would be important to fully land the tieback stem and the tieback sleeve to mitigate collapse, since the unsupported collapse value is lower than the casing value. So when you have pipe in pipe, which is what you call it, when you put the tieback stem inside the tieback sleeve, you get an advantage for collapse by having the pipe in there. So you just have to mitigate, make sure that you retard your cement sufficiently and have procedures in place that when you land your tieback stem into the tieback sleeve, you land it all the way down to protect that sleeve from collapse. This type of risk mitigation would be the type of thing that has to be done all the time. Now, I'm going to start now in casing design criteria. When calculating burst loads, I'm going to say this probably several times, but when we're calculating burst loads, we utilize pore pressure on the outside of the casing for determining our loads. The mud weight is only going to be used in a trap annulus containing mud, such as a tieback stranger casing, but if it's exposed to open hole, we will use pore pressure. Now, when calculating collapse loads on a casing, we're going to use mud weight gradient on the outside of the casing for determining pressure. So if you're calculating burst, you use pore pressure on the outside. If you're calculating collapse, we use mud weight. We want to calculate our load based on the worst conditions. So the worst conditions for burst is to use pore pressure on the outside. The worst conditions for collapse is to use the mud weight on the outside. Now, casing design criteria may come from, any of this list that I put together here. It could be common industry standards that we utilize. We may also have a business unit or field specific standards, or depending on where you were operating in the world, that you might have a specific standard that's greater than the industry standard, and you're going to use the most severe of whatever the standard is. And then you also could have a regulatory requirement standard that is greater than the industry standard. So whichever is the most severe design criteria is what's going to control and dictate the specific criteria that you would utilize for a specific casing design project. I'm just going to give you some typical industry accepted, design criteria. I'm not advocating this criteria, but the criteria comes from a long use by the industry with the experience based, and they're pretty severe conditions that works for our industry. Let's just say that's the way we do it, So it's based on long use of experience that works. So one thing you're going to make sure you need to understand, I've already mentioned this, is that we can have standards that we have burst. Well, I won't go back to that, but we can have burst from drilling conditions, and we can have burst from production conditions. So we're going to have different criteria for drilling conditions than for production conditions. So we need to make sure I've kind of highlighted them with a color so that they would stand out of what you're looking at for the criteria. So the drilling criteria cannot be derived, but are risk-based conditions based on experience. So they're going to be probably from a bunch of older, wiser, gray-headed people who developed these over a long period of time, and they seem to work and protect us. That's why they came from. So burst external pore pressure is what we utilize on the outside unless the annulus is trapped. If it's trapped, I've already mentioned, then we can use mud weight, but otherwise we'll use pore pressure. Internal we're going to use the highest pressure from the list or considerations below determines the maximum internal casing load pressure. So if it's less than 5,000 feet, we use 100% production fluids in a well bore. And we always going to use the worst case production fluids for the geological area that you're operating in. So if you're in a geological operating area that you can have gas, you're going to use a gas gradient. If you're in a geological operating area that has no gas and you only have oil, and so your kick is going to be oil. If you take a kick, that's the worst case, then you use oil gradient. So you, whatever the appropriate gradient is what you're going to use. Okay, so it's based on 100% production fluids in a well bore at 5,000 feet. And it's based on 15,000 feet or greater, 50% production fluids in a well bore. And these pressures are based on the drilling depth of the casing in use. So it's based on how deep are you going below the casing that you're designing to. So if you have a casing that is set at 5,000 feet and that casing is being used to drill to 10,000 feet, then 10,000 feet would be the depth you would use to calculate your production fluid level in the well bore. So it boils down to, at 5,000 feet, it's 100% production fluids. At 15,000 feet or greater, it's 50%, and then you interpolate in between. So for every 1,000 feet above 15,000 feet, you add 5%. So at 15,000 feet, it's 50% production fluids. So if you came up to 14,000 feet, it would be 55% production fluids. But I have put the, the little formula over here that you can use to interpolate to come up with your fluid level in the well bore. Worst case production fluids, oil or gas in the geological area are utilized for the calculation. And limitation, here's something very important. The pressure at the casing shoe is limited to a maximum of the fracture pressure. It's going to be easier to show this on an example than to try to explain it, but we will start calculating the pressures at the bottom of a hole section, borehole section, and then we'll come up the hole using the criteria. If using the criteria, the pressure at the casing shoe that we calculate exceeds the fracture pressure, we will limit the pressure on our well bore to fracture pressure. We won't exceed it, because the reality is there is no way we can have a higher pressure in our well bore than fracture pressure. So you cannot exceed fracture pressure in an open hole section at the casing shoe, because it will fracture. So it won't, there's no way to get higher than that. We also can use a fracture pressure. So there's several criteria. Here's one criteria. Criteria number 2 is a fracture pressure of the deepest casing shoe with a water or seawater gradient down to the surface. I call this the bullheading condition. So you would go through and calculate a load based on number 1 for, let's say, a surface casing or intermediate casing. But then you could compare it to what would the load be if you did it with number 2. So based on number 1, you might have the case if you were drilling the well to, let's say, 20,000 feet. A string of casing is being designed with a fluid level of 50%. So it's based on a 50% fluid level. But yet, on the other hand, if you want to think about another way to look at this problem is if you end up with a well-controlled event, number 2 would be the case where if you had a well-controlled event and over the weekend, you're trying to control this well, circulate it out on the choke, you run out of barite. Let's say you run out of barite, and then the boat is supposed to be bringing you barite to the rig, and the boat has a breakdown, or it gets a rope in the wheel and can't get to your location, or either the weather's bad and you can't tie the boat up, something that you always can do is control the well is by pumping water into the well. So you can, number two is the case where you're doing bullheading, that you're bullheading water, available water into your well. So if you're offshore, you have seawater. If you're onshore, you have fresh water. So you can bullhead water into the well to control it until you get your bay right to the rig, or you come up with an alternative plan of well control that you're going to implement. Now, criteria number three is actually not a design criteria, but it is a limitation of casing application. So casing test pressures are limited typically to 70% burst rating of the casing. It's not a design condition, but it's an execution limitation. We're going to do an exercise on that. So I've never designed casing for a particular casing test pressure, but I choose the casing test pressure that matches up to the casing that I've selected to drill the well with. And then application number four, I won't get into that today, but I just will mention it. Annular pressure buildup, pressures from trapped annuli when applicable, such as a subsea production operations, must be considered in all cases, not covered in this overview. So if you have trapped annuluses that are isolated and you have no ability to bleed off pressures or pressure up on annuluses like a subsea well, you have to predict what the pressures are going to be in the planning of the well, and then choose casing strengths that comply with the annular pressure builds up that you could have based on the temperature effects in drilling a well. But that's out of the scope of this overview. Now, the production case is very straightforward and fairly easy. So we're looking at a production case, and then we're also looking at the burst case. The external pressure is still going to be the pore pressure unless it's a trapped annulus. So it's always going to be the pore pressure on the outside unless it's a trapped annulus, and then you would use mud weight. So for instance, if you had an intermediate casing string, and then you ran a tieback string of casing from a liner down in the well up to the top, and that was a trapped annulus on the outside of that tieback string of casing, you could use mud weight for that case. That's a great example of where you have a trapped annulus. And then the internal, you're going to use the highest pressure from the list below, determines the maximum internal casing load pressure. It's a fairly simple list though. It's based on a tubing leak containing 100% production fluids. So it's not going to be based on a fluid level of partial fluid level in the well of like 50% or 75% production. It's going to be entirely full of production fluid. So when we're talking about a production load case, it is 100% production fluids in the well bore. And it can also be affected by completion fluid weight utilized on the well. And I'm going to show an example of that in the exercise. And then, so it's going to be, like I say, it's going to be based on a tubing leak with 100% production fluids, or case number two is a well treatment pressure during screen out or stimulation. And I've made two examples just to illustrate this that we can see. The one on the left is a well that, let's say, we're doing a gravel pack on the well. We're going to do a frac pack on the well. So we've got a gravel packer set in the well, and we've got drill pipe going down to this packer, and we've got a screen down here, and we're going to be doing this stimulation treatment, let's say at 12,000 psi. So if I'm going to be pumping at 12,000 psi, maybe at 11 barrels per minute, even though on this particular well that I drew up, it's at 10,000 feet. It's at 10,000 feet, and it has a 9 pound per gallon pore pressure, which is only a bottom hole pressure of a little bit over 4,600 PSI. So it's 4,600 PSI pressure, which is pretty low, but my treating pressure is 12,000 pounds. So what happens when you get a screen out and doing a frac pack, you're pumping at 12,000 PSI, and most of this pressure loss is frictional pressure loss is going down this string that you're using a tube and a drill pipe to do this frac pack treatment. It has a crossover tool, so this sand-laden fluid comes down the inside of this treating string, goes outside through the gravel pack packer, down through the outside. When screen out occurs, the pump rate goes from 11 barrels per minute to 0. So when screen out occurs, there's no more pumping into this formation. And when the treatment rate goes from 11 barrels per minute to 0, frictional pressure loss goes to 0. So out of this 12,000 pounds treating pressure, the frictional pressure losses might have been 9,800 pounds. So if you take the 9,800 pounds of frictional pressure loss goes away, now I have this pressure wave going down that's 12,000 pounds that if I don't mitigate it and manage it can rupture this casing down here at the bottom. So the red part of the casing down here at the bottom on the outside of this gravel pack assembly from this gravel pack packer down would be rated to this treating pressure. And likewise, on a condition like an unconventional well, where this is the same well depth I've shown here, this little 4,600 PSI, that if we were doing the treatment down the casing, and let's say we're pumping at 40 barrels per minute at 6,500 pounds, this entire casing string would have to be designed to exceed 6,500 pounds. Even though our rating based on condition number 1 would only be in the range of about 5,000 pounds, the rating based on number 2 would be 6,500 pounds. And so therefore, we would have to have a rating for stimulation of either 6,500 pounds for if we were pumping down the casing, or the lower portion of this well would have to be rated to something like 12,000 pounds to avoid rupturing the casing out of zone. So that's the stimulation examples that I wanted to show. Now, I'm going to switch to collapse now. So if we take a look at the drilling load case for collapse, the external pressure, we're going to use the higher of the pressure that we have in this list. Number 1 is the mud weight gradient on the outside of the casing. I've already mentioned when you're doing burst, you use pore pressure on the outside. When you're doing collapse, you use mud weight. So we will use mud weight on the outside of the casing. And then number 2 is the overburden pressure for the interval of casing through salt. So all salt acts like a liquid distributing the overburden pressure to the outside of the casing. So if we have casing going through the salt layer fairly deep, that's at high enough temperature that's going to have creep, then we will have to use the value of overburden for the interval where the salt is for our collapse value on the outside. And then number 3, it's hardly ever I call it a design issue, but it's something you need to check. It could be extreme conditions the way you do a cement job, and at least something you would check. Use a cement slurry weight outside of your casing before it's set up with whatever fluid you have on the inside. So you could do an extreme casing job, cement job, where you mixed 18-pound cement on the outside of a casing and you displaced the cement with fresh water and you ended up with a real large differential for some reason. I have never seen it in my career to be an issue of any of the wells that I executed on, but it's something that needs to be checked for make sure there's no exceptions. And the pressure on the inside, now this is an interesting concept. It says to use a normal pressure at the bottom of the casing wellbore section as though the well drilled into a normally pressured cave. So the normal pressure means about 9 pounds per gallon for an offshore environment and maybe close to 8.3 pounds per gallon for a land operation without the presence of salt. So if you think about a case, if I had casing set at 5,000 feet and I drilled to 10,000 feet and I drilled into the cave with 12 pound per gallon mud, obviously my mud weight is not equal to 9 pounds per gallon, so the mud is going to fall inside my casing until it equalizes with the bottom of the hole that I have just drilled to 10,000 feet, such that the pressure in that borehole is equal to 9 pounds per gallon. And so you can calculate that value. An example, mud height in the bottom of a well bore is equal to normal pressure at the bottom of the well bore section. So here's an example. A well drilling to 12,000 feet with 12 pound per gallon mud. The bottom hole pressure at 12,000 feet, based on the criteria of 9 pound per gallon pore pressure, would be 5,616 psi. It's just 12,000 times 0.052 times 9. That would be 5,616 psi. The hydrostatic height of 12 pound per gallon mud required to provide 5,616 psi of hydrostatic pressure would only be 9,000 feet. So it's only going to take 9,000 feet of 12 pound per gallon mud to equal that pressure. Therefore, the top of the fluid level in the well bore is going to be 12,000 minus the 9,000 feet of mud in the well bore. So it's going to be 3,000 feet. It's where the fluid level inside that casing is going to be from the top. You can also just use this little handy dandy formula based on, I call it ratios, that the mud drop is going to be equal to the mud weight minus 9 divided by the mud weight times the depth. So you can use that and you'll get the same answer. So it's we'll see that on examples when we look at collapse example that I go over later. Now the production load case criteria for collapse is that the external pressure is, again, it's either the mud weight on the outside of the casing, it's the overburden pressure for salt if it goes through salt, or it's either the cement slurry weight. So it's the same criteria on the outside for production. The internal pressure is real easy to calculate. It's 0. We use 0 pressure on the inside of the casing for a production load case. And here's some possible ways for the internal pressure to approach 0. It's almost impossible to get to 0, but we can get to some pretty low values. The zone could deplete. So you could complete a well in a gas zone, and over a long number of years, it just simply depletes. It depletes. I have completed some wells before and worked with some wells that had a bottom hole pressure less than 1 pound per gallon. So even though they were originally completed with like 13.5 or 14 pounds per gallon equivalent bottom hole pressure, they depleted down to a pressure less than 1 pound per gallon. So that's not exactly 0, but it's going to be a very low number. Number 2, the well sands up near the bottom of the completion, and the surface pressure then equalizes with the surface separator pressure. I've seen that happen before. I've seen cases that seems like it always happens at 2 o'clock in the morning, a choke cuts out, and the rate on a well offshore that's a high pressure well that's on a, let's say, a 1/4 inch choke is producing 30 million cubic feet of gas a day. And at 2 o'clock in the morning, the choke cuts out, and the rate on that well goes from 30 million a day to 100 million a day for 30 minutes. Then the well sands up on bottom, so it won't flow. As soon as it sands up on bottom, it doesn't flow anymore. Then the tubing pressure and the casing bleeds off below the packer to the surface separator pressure, which may be 500 psi. So we've got a hydrostatic gas in the well, and 500-pound surface pressure, which is something close to zero. So that's a great case, and I've seen that happen before, during the night on a producing well. And then number three, we can be doing a weld intervention of a workover using coil tubing or snubbing unit, where we are intentionally lifting the fluid out of a well to try to get the jetting the well in to try to get it to come in and flow. And so that's another, I call it a man-made condition where we actually do operations that can approach zero on the inside. So there's several reasons and ways that the pressure on the inside could at least approach zero. All right, so here's, we're going to switch now to both for drilling and production, axial loads for compression and tension. For axial compression, the entire weight of all the well tubular strings plus intervention or service loads are supported by the structural pipe. So you would calculate all the weights on the well. Let's just say you're going to drill a really deep well, and adding up all the air weights of all the casing and tubing on the well is going to be 4 million pounds. Then you use 4 million, and then you make some assumption about the weight, the loads of a snubbing unit or coil tubing unit on top of it. You would rig up on top of the Christmas tree. Maybe it's like a 500,000 pounds. And so then you would design the compressional loads on the structural pipe up at the top for, say, all of that weight, 4.5 million pounds. I mean, it would be the number that you would use to consider for the compressional loads. Now, the tension is, generally speaking, is the combined load of the weight of the casing plus any additional service loads. So the weight of casing, the way I think of it, and different people could argue with me, but the actual weight of the casing that you're going to support on the hook load, the air weight, is actually going to be the TBD depth times the weight per foot for the casing. So the maximum weight you would ever have on the hook load is going to be the TBD depth times the air weight of the casing. The normal force on a directional well would support any other additional load, And then number two is the service load. The service load could be quite a bit additional load. So I put an A and a B here. A is any operational overpull. It's pretty typical that you would calculate, number one, the air weight of the casing, and then you would also come up with a service load, number two, which is you may use a number like 100 to 150,000 pounds overpull. It's going to be some number based on your area of operations to make sure you don't accidentally over-tension the pipe during the process of running it and putting the slips in and doing all the things that you normally do. So, sometimes people will adjust this air weight number for buoyancy if necessary, but that's a preference of company and a specific operator to whether you want to adjust it for air weight or buoyancy or not. I always just use air weight, but I'm not suggesting that. It's just that if your number exceeds air weight, then you can take buoyancy into consideration. Now, number B is to me, it's a very important consideration. It's seldom listed. It's not even listed on any of this real sophisticated casing design software that we have. It may have a little term here that's got 5 letters to it. It says other, but most of the time it's not even listed. But that's a suspended load in the unsupported portion of the casing string, along with any pressure test load applied to it. So let's give it an example. Let's say you're drilling a 25,000 foot well, and you've got 14,000 foot of intermediate casing in the well. That's was cemented only 3,000 feet of the bottom of that casing at 14,000 feet was cemented. Now you've got a storm coming, and you're going to hang off all the drill pipe on a 20,000, 24,000 foot plus well on drill pipe inside the top of that casing, right near the top of that intermediate casing on a storm packer. And then you're going to pressure up on top of the storm packer with before you disconnect the storm packer, and you're going to do a little pressure test to make sure you have integrity on your BOPs. Okay, so this example, if I were to hang off 400,000 pounds of drill pipe weight suspended in the casing, and then I pressured up on top of the 13 5/8 packer to 2,500 PSI, that would be an additional load of 300,000 pounds. The combined additional load that I would put on top of this would be 700,000 pounds from the drill pipe weight pressure to pressure load. And like I say, that number is not listed on anything. You just have to know that that's what you may do based on your experience of your operation, and consider a 700,000 pounds weight at the top as opposed to this 150,000 pound weight at the top overpull. Whichever is the greater for your operation is what you're going to have to consider. Now, casing design factors are also based on industry standards, business unit specific standards, or regulatory requirements. You're always going to have to use the worst case of wherever you're operating based on whichever is the most stringent. Here are some common industry design factors that I will just review. For burst, we typically use 1.1 design factor for sweet service without H2S. So 1.1 is pretty common. I'll go over some examples of that when we do the casing design examples in the next video. We typically use 1.2 design factor or safety factor. Some people call it a safety factor. If we're in an area in which we can have the presence of hydrogen sulfide. So if we have casing that can be exposed to hydrogen sulfide and we're designing it for sour service operations, we typically use 1.2. Now here's a note I put here about why do we use 1.1 versus 0 or some other number. The highest drilling related burst loads would generally be at the top of the well, close to people and the environment, thereby requiring a higher design factor to mitigate potential problems from burst. I have already said that using the API equation gives us, that's already an extremely conservative number, because the yield strength is going to be greater than the minimum. The wall thickness is going to be greater than the minimum. There's many factors that makes it great. And then the formula itself is conservative. So it's always going to have a much higher burst rating than the API rating. So, but we still will use a 1.1 safety factor for choosing casing strength. Now, collapse, we typically use a value of only 1.0. And the reason why is good reason. From a practical perspective, it's difficult to get close to the criteria design collapse loads in the real world other than human error, in following a procedure. That is about the only way you can ever get to close to the collapse design criteria would be a human error. And we can't always design for the absolute human error and having 0 inside of all casing strings. We just don't do that. So the highest collapse loads will also be near the bottom of a well bore, away from people and the surface environment. So therefore, it won't be exposing this risk to people or to the surface. So if something were to happen from collapse, it's going to be away from people, and it's going to be at the bottom of the well bore. So it's not going to result in a surface environmental incident or a potential impact for the people on the rig. So that's kind of where that comes from. Now, in tension, we typically will use a design factor, and an example helps illustrate this in a good way. 1.3 to 1.6. So we kind of use a range of 1.3 to 1.6. The value of the extra tension above actual weight must be sufficient to mitigate any potential unexpected overpull during execution. So let's, a couple examples. Let's say we run in 7-inch, 26-pound casing to 10,000 feet. Okay. The air weight of that casing would be 260,000 pounds. Okay. So if we wanted, just for safety, to make sure the driller doesn't make some mistake or something, if we wanted 150,000 pounds margin of error in overpull, we thought that was acceptable, then the design factor would be 150,000 divided by our air weight, 260,000 pounds, plus I call it the factor of 1. So we would need a 1.6 safety factor for that application. So we would have enough, we would be designing in 150,000 pounds overpull. But yet, on the other hand, if we were running 11 3/4 casing, 65 pounds per foot to 14,000 feet, the casing air weight equals 910,000 pounds. So even using a larger number, if we thought 250,000 pounds of margin of error for overpull was acceptable, and we were not going to be hanging off any drill pipe in that well bore for based on our experience in the area or anything like that, then 250,000 pounds overpull divided into that 910,000 is equal to only 0.3 extra. So we could actually use a design factor down to 1.3 and be acceptable and be safe for that particular type of casing string. So it's going to be based on your operating area, and most of the time different operating areas would choose values based on experience somewhere between 1.3 and 1.6. They may use 1.6 for the upper casing strings, and then when you get to the deeper, long intermediate casing strings, they may use a number less than 1.6. It's still going to be safe. For compression, we typically use a safety factor of 2. A typical safety factor is to utilize for that upper structural pipe compressional load, which supports the entire weight of the well. The last thing we want to have happen is to be drilling a 25,000 foot well, and then we have reached 25,000 feet, run our production liner on the well, then we run in a production tieback strainer casing on the well, and we run that casing, we land it, and then the whole wellhead assembly falls down 4 feet. That's a really, really bad day. So you want to make sure that you design, I call it your foundation, which is those structural pipes with extremely good integrity, not to cause you a problem on day 110 of a 120-day well, which is you're going to lose the entire well if you have a problem at the bottom of the well. All right. Now, generalized casing design procedure. Casing loads are based on criteria calculations. So we'll calculate the casing load based on the criteria calculations, and we'll see that with examples that we're going to take a look at. We multiply the casing load times the design factor to get the casing design load. So for instance, the design factor for burst is 1.1. Design factor for collapse is 1.0. So the collapse, I call it safety factor, doesn't change anything typically. And then we choose a casing specification or casing strength that fulfills the value that we get in our casing design load. So we choose a casing specification that has the required casing strength. So that's the way we do it. So we calculate a casing load in the beginning, we multiply it times the casing load times the design factor to get the casing design load, and then we choose casing strength that has a value over that. So for burst and collapse, the typical way you would do it is you begin with the wellbore diagram that I've already shown, showing TVD depths, pore pressures, mud weights, and shell fracture gradients. You draw a diagram of the wellbore based on the design criteria showing the fluid level and gradients in the wellbore. So if you have a fluid level that's 50% in a well based on the criteria, you draw a line where that fluid level is, and then you, for burst, number 3, you start at the deepest depth for casing to be utilized, and you calculate the wellbore pressure at that depth. And then you calculate the hydrostatics coming up the hole from that point, and you calculate at each node the pressure on the inside of the casing as you come up the hole all the way to the top of the well. For collapse, you calculate the pressure on the inside from the surface down. So in other words, collapse is based on a mud drop. So you're always going to have zero pressure at the top of the well, and you're going to have zero pressure wherever the mud falls to, and then you're going to have the hydrostatic of the mud in the wellbore down in the wellbore below that. So you're always going to start at a point where you have a known pressure. So for burst, it's going to be the bottom hole. I call it the pressure inside the wellbore based on pore pressure at the bottom of that borehole section that you're calculating. And then for collapse, you're going to start at the top with zero pressure and calculate hydrostatics going down. And then once you've calculated the pressure in number 3 on the inside and the outside, you calculate number 4, you calculate the differential pressure at each node to determine the casing load. So you're going to have a pressure, let's just say at 10,000 feet, you have a pressure on the inside of 8,000 PSI. Okay, at 10,000 feet, it's 8,000 PSI. On the outside, you have a pressure at that same depth of 4,000 PSI. So therefore, your differential pressure would be 8,000 on the inside minus 4,000 on the outside, which would give you a differential pressure at that depth of 4,000 PSI. Then number 5, you multiply the design factor. So if it was burst, you would multiply that, the one I just illustrated, at 4,000 pound casing load times 1.1 to give you a design load of 4,400 pounds. So that would be, then you got to verify that the most stringent criteria is met. So you would calculate it based on a drilling criteria, but then you might check to see if the criteria is a worst case for bullheading or some other criteria. So you want to check all the criteria and make sure you're using the worst criteria for that application in choosing the casing strength. And then number 6, you would choose a casing strength, size, weight, grade connection that meets or exceeds design load. And then you will verify all 3 loads are satisfied: burst, collapse, or tension. So you may be doing burst first, and then once you've completed burst and have chosen the casing for that is okay for burst, you've got to verify that it is satisfactory for collapse and tension as well. So whichever you do first, you have to still verify all 3 of them. And then for tension, it's the weight of the casing. You multiply the tubular weight per foot times the TVD depth to get the air weight. And like I say, the air weight is based on TVD because the normal load of a directional well holds up the additional weight. And then the service load, you add a business unit specific service load to it, which is going to be some, number A is some amount of overpull that I've already described, you know, to make sure you don't accidentally overpull a casing. And then B is that suspended load in the unsupported portion of the casing due to like hanging off drill pipe on a storm packer, something like that. And then number 2, you multiply the design factor times the maximum tension load calculated to determine a casing design load. And then you'll choose a casing strength that is okay, that is satisfactory for that design load. So, and I've already mentioned other, I call them learning practices. And here's another one that I strongly encourage. I strongly suggest to utilize casing slips that have the same tensile rating as a casing strength to avoid operational overloads during execution. I have seen the case where a vendor asks you, how deep are you running casing and what's the weight and grade of it? You say, okay, I'm running 60-pound casing to 10,000 feet. Well, they can do the math. That's 600,000 pounds. And so then they choose casing slips that's good for 600,000 pounds or greater than 600,000 pounds. But no one asked a question about hanging off drill pipe inside of it or pressure up on a storm packer, and then you end up with 1.1 million pounds load on the slips when you pressure up on it with a storm packer, and then you collapse the casing and you can't get back through the casing with a bit because it's partially collapsed your casing at the top, deep in the well, on day 105 of a 120-day well. So if you use the long casing slips, which are rated the same as the casing, it prevents you from having those kind of mistakes happening. And again, even if you've done tension first, you need to verify that all 3 loads are satisfactory: burst, collapse, and tension. Now, the last part in this section that I'm going to go over is the sequence of doing casing design work activity. For the drilling load case, so if you're doing a casing design for drilling load case, it's always best to do them in this order. Do your burst load case first, then do your collapse load case second, or check it, and then do axial load case last. And the rationale for this is that if you look at casing specifications, the highest drilling loads are the burst loads at the top of the well from the drilling environment. The collapse rating for a particular casing string that meets the burst condition will be close to the burst value, even though the collapse at the top of the well is very low. So in other words, you're going to have your highest burst load at the top of the well, but yet you almost have no collapse load at the top of the well. So the values for collapse, they mimic, if you look at the casing strength chart, are generally speaking, they're pretty close to the burst loads. And the burst loads, the collapse loads for drilling are actually very low anyway. They are a lot less than burst loads. So generally speaking, it's suggested to do burst first, then check collapse, and then check axial loads. The only exception that I can think of that I've ever had in which tension load was a driver, and that is on a normally pressured ultra deep well. So if you were to drill a 20,000 foot well with 9 pound per gallon mud, it would have a bottom hole pressure of about 10,000 pounds. It's about a half a pound per foot. So that would not be high strength in terms of burst or collapse, but it would be probably driven by a tension load case on a really deep, normally pressured well. But that's pretty much an exception. I haven't had too many wells that came into that he applied for, but it does occur on, like I say, an ultra deep, normally pressured well. So the applicable casing strings that this, I call it suggestion, applies, since it's for doing, it's for the drilling load cases, it's all the drilling casing strings that are only being utilized for drilling the well, which would be conductor casing, surface casing, and intermediate casing strings. All of those casing strings, if they're only being utilized to drill the well, then you do them in that order. Okay. So then the production load case would be, I suggest, to do collapse load case first, and then do burst, and then do check axial loads. The worst load case on a production load case is that collapse load of 0 on the inside. Since collapse loads are highest at the bottom of the well and there's 0, it's probably going to be a driver on a particular, if it's a high pressure type well. So do your collapse design first, select a casing that is sufficient for collapse load, then check burst, then check axial load. Like I say, the highest load case for production casing is generally collapse, since it's designed for 0 at the bottom of the well. The same exception for the drilling load case is that the only likely exception would be an ultra deep, normally pressured well in which both the burst and collapse loads are low, such that the tension load may become a driver. So the applicable casing strings in which you'd want to do them in this order would probably be like your production casing, designing the production casing, which is obviously going to be a production load case, or a production liner. All right. Hope you have found this to be very helpful in understanding, casing design criteria and the general order in which we do casing design work. In the next video, we will go over some casing design examples using the criteria, and I highly recommend that you print out the notes, follow along on the notes where you can be easier to visualize the process as we follow along on those notes when we do casing design examples. Thank you.